Harness. And I work with all of our partners. So, my focus really is DevOps overall. My background is actually quite diverse. I'll talk about it in a moment. But the talk for today is really about delivering continuously with confidence, right? So that's really the idea. Utilizing machine learning to help you feel confident in those delivery models. If you want to reach out to me, my my contact info is there. You're welcome to either email me or you could tweet me if you need. But let's jump into this. So who am I? Well, I'm not a data scientist, so I will talk a little bit in depth about the machine learning that and where machine learning plays its part in continuous delivery, and I'll talk a little bit about the algorithms, but I don't have a PhD in mathematics in that regard, so I don't consider myself a data scientist, but I'm going to really talk about the practical knowledge here. But historically, I currently work at Harness, which is focused on continuous CI and CD, continuous integration and delivery. But prior to that, I was in the APM space. I've worked for a storage company. I've worked for embedded systems companies for years. I've been in the retail and in the web sphere for quite a while. But basically, all of what I'm applying is the practical knowledge that's drawn me to a DevOps kind of career, as well as an understanding of machine learning in this delivery model. So what is delivery done well? Well, I like to think of it almost like a meal. If you go to a restaurant to purchase a Michelin star meal, what you're really looking at is the culmination of experience and practice, but also a very well and clearly defined process. And that process is what delivers a perfect meal every time to the customer. And since delivery, especially even in software, is really about delivering to the customer, I thought this would be a proper analogy to bring to the table here. So let's talk a little bit about this. Cooking is not necessarily delivering food, but cooking has some unpredictable results. And too often we see very poor delivery of this, right? So maybe it's not a good, hasn't been practiced. There's not good quality assurance. Maybe someone's not using the right ingredients. They're not following a recipe, things like that. So all of these pieces that come together to form a delivery of a good experience doesn't always appear. And sometimes it's just poor execution overall. So when we look at the idea of delivery, we want to look at it in the context of a chef's recipe, right? We want to follow a recipe. We want to follow a well-defined templatized model to make sure that every time I go, I serve my customer, they're getting the best of experience. So let's look at what that process looks like. When we have a recipe here, we have a new recipe. We want to get it to the customer, to the value, right? And to provide that value, we have our Michelin delivery pipeline, right? We want a 3-star pipeline. And so when we start, we gather the best possible ingredients and prepare that new recipe. And this is the first time we're going to do that. And then so think of it like we're delivering something. We're going to put all the pieces together. We're going to test it out, whether we subject our coworkers to a peer review, whether we push it out into social media, et cetera. We want to kind of get feedback on our idea, right? This initial recipe. And then once we've completed that, we're going to start to deploy this. And the deployment may not be perfect in the beginning, but we want to deploy and continuously improve this. So we deploy it, we evaluate it through the value, to our customer, and we verify that we're doing well post-production, right? Post reaching our customer. We want to make sure that it's successful and it continues to be something that is valuable and the customers want. So they're receiving essentially the features and the value that they expect. And when they're not, we want to have the ability to roll that back. So I used to have an interesting kind of workflow for this where I would liken it to, and this doesn't necessarily always translate globally, but in what we call the Chinese food takeout model, right? We package up in a container, we move that container, through the process. We take the food, we put it into the container, we deliver the container to the customer, and when they are unhappy, the solution, especially today, is we would actually throw that out. We wouldn't ask them to return it, and we'll fix it. What we actually do is we have them throw it out, and we deliver a whole new recipe, a whole new container through that process, through that pipeline. And this is essentially that pipeline, right? We're delivering it to the customer. The customer is unhappy. How do we quickly resolve that? Well, we resolve that by starting a new meal through the pipeline and delivering it to the customer. And that's kind of how we want to focus on this. So how does that look? Well, today in a restaurant, it could take days, if not weeks or months even, to create a good recipe. It takes a long time to test through that, maybe a few minutes to deploy it. But ultimately, it could take minutes or days or even hours, maybe 8 hours if you don't produce good food and the person gets sick. It could take several hours, but ultimately you want to be able to roll that back quickly. You want to be able to resolve it and make sure that you don't lose a customer. Because in the restaurant industry, at least, customer acquisition cost is incredibly high. And especially at the highest level of these Michelin restaurants, a lot of customers come once or twice. They don't come over and over and over again. So maintaining and retaining that customer is incredibly important. So let's talk about those ingredients. When you prepare a meal, for this particular pipeline, you want to make sure you have the best ingredients, the best of breed of your ingredients. So the freshest organic vegetables, the fresh harvested fish, if you're a meat eater, then the Wagyu beef, right, for instance. And you want to make sure you have the best of spices and ingredients that you're importing in. You don't want to, put anything substandard. But your recipe can't be ad hoc. It can't be scripted, right? It can't be a scripted recipe. It has to be a really well-defined recipe, right? With exactly the steps needed to produce this meal and produce this delivery for your customer. And it's the same then for software. So I know I've kind of dragged you through this, but I want you to understand where this analogy goes, right? We want to make sure that you're providing a successful delivery for your customers, whether you're using the best ingredients and best of breed products. And what a delivery pipeline should look like is that you should be testing and verifying within that pipeline all the way before and after delivery to a customer. So how does that pipeline look? Well, we start with the best ingredients, right? We build it with the tools, the integrations that we have, whether you're using Jenkins today, or if you're looking at something like Drone, which is one of the more cloud native solutions, or you package those up and drop them into Artifactory or a registry. That's where you're going to build your ingredients. Then you're going to test it, and you may be using Jenkins in your testing phase, but you're going to want to test it for security. You want to test it for lots of different components here, but it's kind of automated. A lot of times what we're finding is the testing in your pipeline is somewhat manual, but for the most part, Selenium, things like that are somewhat automated. But then we get to the deployment stage, and this is where it all becomes a very manual process. And the thing about deploying in a manual way is that you wind up with a lot of custom scripts that make things very brittle. You also wind up with a lot of user-prone errors. If users are making configuration changes live and ad hoc, you could wind up with some very unpredictable results in your deployment. And your customer, of course, may or may not be happy, but we want to validate that or verify that. And we can use APM solutions like Instana or logging with Splunk or Dynatrace or others to identify and verify that the end user and that the code that we've deployed is actually successful. But still, the challenge is that analyzing that and looking at that data may be automated, or analyzing the data may be automated by some of these tools, but actually applying that verification to your pipeline is still somewhat of a manual process. And that takes a significant amount of time, and also could be prone to errors as customers may miss things. And finally, that rollback. When things don't go right, maybe things, errors or bugs might have slipped through into production. That's where you have the WTF moment, where you have to figure out, how do I unravel all of this and get this back to a start, back to a perfectly running example. And when everything's manual, then the manual result of rolling back becomes a very time-consuming and challenging issue that actually could impact customers. And again, even in the software industry, or in any industry that's using software, which is really what we're focused here on, those customers are expensive to acquire, and they're also expensive when they leave. Sometimes they leave in ugly ways with tweets, and that could also have some very downside effects on the business. So really, when we look at this, our food delivery pipeline as well as our software delivery pipeline really are about driving value to your customers and making sure that your customers are successful and the value was successful for the business, because otherwise the business is the one that suffers. Programmers and developers and infrastructure folks suffer as well, but ultimately, yeah, the business is what we're focused on here. So this could take, if you look from left to right, minutes for the automation, but hours, days, or more as we move from left to right. So this is really what we're trying to solve with continuous delivery, because we want to be able to deliver this in a very automated way from end to end, from the CI all the way to the production state. And we want to drive that value to our customers and not impact the business. So today, traditional verification is, noise level monitoring. Maybe somebody's going and looking at something, right? Has anyone complained? That's what we call noise level monitoring. Somebody looks at the homepage, but did they actually apply any of the business functionality to make sure that it's actually working? Or is the alerting set up? Do we get the right information? We're not seeing any alerts, so there's probably no issues. This traditional verification isn't ideal, of course. So how do we address this? Well, first, you need to automate everything. And automating everything includes everything from your integration, all your unit tests, all your integration tests, any of the testing that you have to do in dev, moving that over on success, moving that over in an automated way into your QA, where you're doing all your smoke tests, your regression, security, etc. And finally, completing that up is moving it into production. When everything is successful, move it to production in an automated way so that you don't have to have manual approvals or manual reviews of all of this information. You should confidently be able to see that all of those tests were completed and that they were all successful. And on that success, be able to move it into production confidently, because all of the production testing that you're doing is going to be via things like Canary or Blue-Green, and making sure that the code is delivered without error to production, to the customer. So all that value and all the features that have been kind of developed from stage one, make it all the way through into providing value to the customer as quickly as possible. Because value or features that are sitting in Dev or QA are not providing any profitability or value to the customer itself. So when there's an issue, you want to, of course, be able to deal with that very quickly, and you want to be able to roll those back if there's an issue. So how do we do this? How do we kind of work through this? Well, we're going to use machine learning, but we need to understand that machine learning is not magic, right? It's not, it's using data science, it's using math to identify things that you need to see. However, math is also not a silver bullet. Machine learning can use patterns and use different algorithms to better identify things that humans can't, of course. It's not a silver bullet, obviously, so we need to make sure that when we see problems, we can address them quickly, and that's part of the continuous delivery story as well. But when we're looking at machine learning, we want to understand that it is data science. It is using math and algorithms to help identify and reduce the amount of noise so that you can identify those problems quickly and address them. So let's dig into machine learning a little bit, since that actually was what the talk is about. So first, there's something called unsupervised machine learning. Unsupervised machine learning is really about letting the algorithms do the work, right? Letting algorithms figure out what the context is and making their own natural decisions on this. And there's things like, natural language processing, where it's actually analyzing the way and the intention of the words that are being used. There's neural nets, which is then mapping all of the different interactions between those different observation points and different and building of that context. And that's kind of how unsupervised machine learning works. There's the supervised machine learning model, where the algorithms have been created, but maybe there's some nudging, right? There's some training that's going on, utilizing training models, for instance, where the algorithms are used to develop an identification pattern or help finding those patterns, as well as the additional feedback from the users. So whether or not this particular pattern that it found is something that's relevant or should be ignored. So those types of supervised machine learning is still utilizing the algorithms and still utilizing machine learning to do this, but it's using human intervention to help guide it in the appropriate way. So supervised machine learning is an important part of this story as well. But there's definitely not rules, right? You don't want to create thresholds or regex, commands. We don't want to say if then statements. We don't want to utilize just standard deviation of, where we say plus or minus 5% is acceptable. These are not machine learning, right? Machine learning is utilizing these algorithms, utilizing the math to identify the patterns, not utilizing human defined arbitrary thresholds or configuration changes. So how do we apply this? Well, when we look at a continuous verification, we're going to utilize unsupervised machine learning so we can instantly identify problems, right? This is kind of the way that Harness approaches it. We're going to look at utilizing this in a way where we're connecting to the existing monitoring tools that are out there, evaluating the business results of this, trying to identify anomalous behavior. And when we see that anomalous behavior, for instance, the revenue for the business has gone down, then we will roll that back, right? We're automating the understanding of whether it's availability, performance, quality, or those business metrics to be able to verify and validate that it would work. And in a pipeline, a delivery pipeline, doing this at multiple stages, whether it be at the QA, the dev stage where you're doing some of your initial like static code testing, whether when you're doing it in QA as part of your initial like stage testing, right? Maybe your load tests and your sync tests, things like that. And then of course, when you're moving into production, really being able to very quickly identify those problems based on the revenue, right? Based on throughput, based on the different outputs that we see. And when we do that, and it's all automated, the results that your teams can now deploy faster without having to really worry about failures in production, because that rollback is automated as well, right? We want to be able to automate all of that. So you can kind of think of when we're talking about Harness, you can think about it as a safety net around production applications during those deployments. And that's really what we're trying to provide, is that confidence during a deployment. So there's a couple ways to look at the data that we're going to analyze here. So there's the context, right? The context would be, for instance, the application we're looking at or the artifacts that we're deploying, the infrastructure on which we're deploying it to, whether it be, for instance, a cloud or in, data center servers, maybe it's Kubernetes, things like that are really important. And ultimately, then we're going to have some control data, which is something that's required for all machine learning. And control data can be based on some previous tests or deployments, or currently running canary functions. So we're doing a canary against existing running running applications, and that'll give us a baseline, for instance. And utilizing that baseline, then the harness algorithms, for instance, could utilize those baselines to evaluate the test data. And the test data could be the new deployment, the new test, or the new canary that's been deployed. So really the goal here is to take that context and measure it against our control data and our test data. And this is where machine learning takes hold. So for harness, we use in the metrics side of this, right? So when we're looking at it from a strictly like transactional metrics or infrastructure metrics, we can use all of the best of breed solutions that are out there, whether it be AppDynamics or SignalFX or Instana or Prometheus or others, or anything you come up with. So any time series database or time series metric that we can draw from, we can evaluate those metrics. And how that looks then is in the pipeline, we see our end-to-end from left to right. We work through from, if we look at the pipeline at the top there, and I'll actually show you this in the demo in a few minutes, but we work from left to right, and we're showing kind of the analysis here of New Relic, in this case, where the performance was good for a particular endpoint that's been evaluated, and that's been evaluated using algorithms that we'll talk about in a second. When we see a regression, of course, that's where we see that, for instance, the average response time for this service is not performing well. And that's evaluated based against, using the algorithms against a baseline. What is that baseline? We'll kind of discuss that in a moment. But if we're doing it in a canary, it would be against the existing kind of running solution versus the container canary that was pushed out. In that case, in this scenario, I'm talking about in Kubernetes, of course. It could be also with AMIs or with other VMs, but ultimately the application itself is being evaluated by New Relic, and we're identifying this regression. When we look at it from something like AppDynamics, AppDynamics has the ability to analyze this from a business transaction model, so we can actually look at the business value. So we can see, for instance, that the previous revenue was at the $14,000 a minute, and now we're at $3,200 a minute, which really is showing a loss if we were to extrapolate that out to, like, I don't know, $600,000 an hour of value that's being lost to a company. So that's a really important regression to identify quickly and resolve and revert. So that's where the rollback phases come into play, and that needs to be automated. And one thing we'll talk about with Harness is that when you do the deployments with Harness, the rollbacks are automated as well, because Harness knows what it deployed, so it can unroll it back to the previous state. So that's an important thing. Okay, so how do we analyze these metrics? From APM, we take our, the timestamp and the values of the particular metric, and we apply algorithms. So one algorithm that we might use is SAX, so symbolic aggregate representation. And what this is really doing is analyzing the variation between two different sets of data points. Now, you can only do this on time series metrics, right? Symbolic aggregate representation. And it's defining really the probability of the risks based on those aggregates. But the con here is that it's really not ideal when applying against production data, which is more randomized. So you need to apply other algorithms as well. Otherwise, you're going to get a lot of potential false positives. And the reason being, if you look to the left, right, we see the metric change to be fairly radical on that green line going up to the left. But if we look at it over on the right here, that difference between the distance, right, between D and B is quite significant in those yellow areas, as well as from the left and on the left and on the right. And so how do we analyze that and not have a false positive with those? Because we're seeing that we have a probability that there's a problem, but we need to analyze that a little bit deeper, and we'll do that with other algorithms. And another algorithm that we might use, for instance, would be the hidden Markov model. Now, for those of you who aren't aware of what a hidden Markov model is, it's really helping you to identify based on a context, but it's really all around the outcomes, right? So when we looked at the previous set of metrics, it's really the path that we're looking at is strictly this metric of this type for this timestamp against this other metric of this type from this timestamp. And those could be patterns that are shifted, right? So even though they're happening, apparently happening or being balanced against a similar time frame, they may or may not be the same metric, right? They may be, it may be traffic difference, right? In the symbolic aggregate, we're looking at it in a time series span, and that difference between those metrics could be shifted, right? We may not have the same type of traffic all the time, and so we wind up with very with very high entropy, and then we'll talk about entropy in a moment. But that high entropy can be addressed or at least overcome a little bit when you apply something like a hidden Markov model, where now we're actually looking at the probability of a pattern, of a thread. So what we see is, for instance, when it's raining out, right? I might be only 10% willing or probable to go statistically to go for a walk, whereas I might more likely be 50% more likely to go for, and clean my house, right? Or maybe go shopping, 40% to go shopping, right? So this is really helping us to understand the probability of those outcomes. So those outcomes are really, when we look at the context of a particular set of metrics, we're looking at, a distance horizontally, right? From where we started to where we're going, not just the time specific range where those metrics occurred. And this allows us to then predict when our data is incomplete. So if we're looking at those time series metrics, we may identify those patterns and match those patterns in our control. And then later, when we're applying something like a hidden Markov model, we can say, okay, well, I don't know how we got here, but these are the patterns I've seen in the past. And these patterns are driving me to assume that this is what my outcome is going to be. Is there a question, by the way? Sorry. Okay. By the way, if there's a question, feel free to ask it. I'd be happy to try and answer those questions, in context if needed. So in any case, so these two algorithms really work well with time series analysis, but they don't work well for things like logs. And Harness is also looking at logs as part of this. So we can utilize log analysis and using ML on those logs to identify anomalies as well. However, logging can't use the similar, the time series analysis that we did before, because log errors and the types of errors we're going to find are going to be far more unpredictable with a lot higher entropy. And we'll talk about entropy in a second, but a lot higher entropy than, for instance, time series metrics. So we need to really look at it from a matter of, for instance, clustering. So let's look at this from the Harness design. When we look at it from the Harness kind of pipeline, what we're actually seeing is a transition from the metrics that we saw in New Relic to the regressions that we see in the logs. So identifying these patterns, or these where the log errors are occurring, things like in this case, a stack trace, and what those error regressions look like in a pattern scattered across this graph. Now, this particular graph is not ideal because it's really a multi-dimensional analysis that's being represented by a two-dimensional view. So we have to think of things like, how are these kind of measured? How are they discovered based on their number of times they're coming up, the location of those errors, the context of those errors, where are they coming from, and all of that plays a part. And then we utilize things like k-means clustering, which helps us to group those events based on the similarity of the messages themselves, right? So we're able to then utilize a k-means clustering to identify where there's anomalies or where there are events that we are familiar with or that look normal to our patterns. However, just grouping them together doesn't necessarily solve the problem, right? Grouping things together really just kind of gives us some pattern visibility, but it doesn't help us to understand if there's a true anomaly here. So when we look at this from the context of k-means, it's simple, right? A group of similar points together, discovering underlying patterns. And we're looking for a fixed number of clusters in that data set. So we're looking at the data set and trying to build patterns of those data sets that we see. So when we kind of move over from this to the view that we saw earlier, we can see on the left here, this Splunk evaluation, and on the right, this Elastic one. Now, what's interesting about the Splunk one was actually, this is a view that we took of an existing, when we tried to deploy out one of our authentication classes, we identified very quickly a lot of anomalies, a lot of unexpected frequencies of varying messages appearing. And then we saw the usual stuff over on the right. And the problem is, of course, that that's a lot of notification, a lot of false positives, because that set of classes actually weren't errors. We just didn't know about them. And so they were immediately, based against an existing baseline. They appeared to be just a lot of noise. However, over on the right, when we look at this and we apply the algorithms that we have before, not only the k-means, but I'm going to talk about another one in a moment, including visibility of that entropy, we're able to then break it down and show kind of, this is what's the usual stuff, right? And here's what's the anomaly. So really reducing the noise is a big part of that. So we need to take entropy into account. Entropy being the more we see something, the less relevant it actually is, right? In many cases, because it becomes more normalized. And really, what we're looking for is the thing that's not, right. The thing that stands out. That's really what we're looking for in a high entropy state. Is when you have a lot of changes, a lot of differences, we want to be able to identify those anomalies and those differences. So here's a little bit about kind of entropy and just a quick, brief about it. We have very low entropy on zero, right? Because zero is the one thing that's sticking out. So we want to identify this low entropy point. When you have a lot of high entropy, meaning a lot of the same thing, then you're going to have this one. So we want to basically be able to identify this difference of when patterns or when anomalies that we're discovering are common or not common. And that's an important part of a lot of these algorithms, because while we're human and we say, oh, that's really simple, I see a zero in the middle, from a computer's perspective or from an algorithm's perspective, it sees a lot of ones and then it sees a zero. It also takes into account, of course, the position of the zero. Where is that zero in the list of ones? Was it early? Was it late? Is it in the middle of it? So this is something that is really important to think about when you're talking about the frequency of issues. So let's look at this from a simple example. So we have an application log. It's got 100 events. Maybe they're thrown in all different places. They're not all the same. And maybe, it's happened in class A, it's happened 100 times in 5 years, right? But in class C, it might be the first time it's happening. And we want to know what's the most important, what was just changed. So we see those changes, right? Those null pointer exceptions in the cluster, but they're thrown in different places in the application. Different positions are relative to each other. And if we remember from the k-means clustering, we had 3 different kind of clusters. What we're really looking at is those changes, those clusters, how big and frequent are the different elements in those clusters. And that's an example of how we're identifying that entropy. Is there more or less null point exceptions thrown in the different places that we're looking, the different clusterings? But that, again, will only identify for us that there's some entropy in those clusters. What we really then need to do is we need to introduce something, to break apart some of that noise. The entropy helps us to kind of avoid some of the noise, but now we need to use a different algorithm. And this is where we use, for instance, the Jacquard or the cosine distance algorithms. And really what they are doing is helping us to calculate the similarity of those nodes where we're seeing those patterns, right? So when we see those patterns, what's the similarity of the context of the data that's in those, or the attributes that are in those particular patterns, and then we can measure the weight and the distance from those clusters. So when we see a number of errors that are occurring outside the cluster, but have similarity of the patterns, then that helps us to identify that there's some anomaly because it's outside the cluster, but it's similar to a pattern that we've seen in the past that should be inside the cluster. So this is where we're looking for those types of distance from those particular attributes. This stuff gets pretty deep, but if you have if you have any questions, again, we can definitely discuss them a little bit. So we look at this simple example. We see, for instance, here that this is a perfect Jacquard distance, right? We're seeing that the diner not found, if we're looking at our restaurant, the diner not found exception, those are all in the cluster where we expect them to be found, right? However, when we look at k-means clustering, it's not perfect, right? The k-means cluster then looks at this and goes, well, okay, we see these together, but the entropy is different because they're coming from different account IDs. So because they're different account IDs, they're coming from different places. They're representative of different executions or different errors. And therefore, we have a high entropy here because of that difference, right? They're not the same. And that actually then allows us to, this creates that noise in k-means, but with together with the entropy and the cosine distance, we actually can say, well, they're not really a problem because we see that they can be, that they're a similar pattern and similar, even though their entropy is high, they have a similar pattern in the expected area that we would see. And then the challenge, of course, is neural nets. So for those of you who've kind of had some experience with neural nets, one of the challenges that you have in neural nets is that it looks for, trying to build some sort of pattern model and trying to build a neural net where it's looking at time series data that just doesn't make sense. You have these weird outlier clusters, and you're just going to get a lot of noise and a lot of false positives because that entropy, where they all kind of look different because they're outside of the cluster, is the challenge, right? So we don't, that high noise is not really a good way to look at it. So in real time, we look at the new attributes in real time and filter those results further using our neural nets. But neural nets, again, are seeing this really ugly space. So we have to train that. We want to create a neural net that is going to be trained and will actually be able to say, okay, well, these are the errors that are outside of the graph that aren't noise. And we need to identify those particular errors as being significant and worth our observation. And we need to do this in a neural net without actually having humans involved, right? We want to be able to do this in an automated way. And these models need to be real time. We can't do this based on historical data. We can't look at this over time because the challenge we're looking at over time is data and the frequency of that data and the amount of transactions that occur. That changes so radically over time that it's not going to be reliable to build a pattern based on historical data. We have to build it based in real time against these models. So, 2/3 of the deployments to build, the neural net, 2/3 of a single deployment during our training model will be to deploy, to understand what that neural net looks like. And then we'll build that neural net, in an automated way so that we can see those patterns very, very easily and very quickly. And finally, when we see those patterns, we'll roll that back really quickly. So that's kind of the key here. And I'll demonstrate a little bit of this for you with Harness. When we see a problem, we want to be able to roll that back immediately. We don't want to have to wait for somebody to figure out that it's a problem and then have to go and look at the data to figure out how to roll it back, which is the service that needs to be addressed. And how do we get the service to production? How do we get it out of production and replace it with a working version? Where's the working version, right? We don't want to go there. So the whole idea here is to roll this back very fast, and Harness does that as part of the rollback phase of our failure strategies. Okay, so what did we learn? Well, we learned that in the beginning of this story, we want to make sure that when we're developing our continuous delivery pipelines, quality is the goal, right? The customer's success is the goal. Achieving the ability to provide really good quality to your customer, whether it be through your shift left mechanisms of taking earlier, results and applying them back to the beginning of the pipeline, or dealing with it to make sure that customers are not impacted by problems with things like the deployment strategies of Canary or Blue Green or others. Really just the idea here is make quality of your code the goal, the quality of the code that you're putting into production. To do that, you want to test early, you want to test often, whether you're doing integration tests or soak tests or you're doing performance testing. You want to make sure that you're testing earlier in your pipeline. This is a shift left strategy. The earlier you test, the quicker you can solve the problem, the quicker you can fix an issue, and you can make sure that it's not going to be deployed out to impact your customers. So that's a huge part of testing early and testing often to identify those problems before they reach a customer. If you automate this and you're utilizing a solution like Harness with AI and ML built in to the solution to verify your pipeline code as it's deploying, then you should be able to trust your pipeline. So you should be able to deploy confidently and make sure that you are producing the best quality code that's fully tested, and your pipeline will resolve it if it's a problem. So, I mean, think of it almost like if I want to deploy on Friday night at 6 p.m., I don't have to be worried, because if there's a problem, the system will automatically roll me back to the working state, and then we can just wait till Monday morning to deal with it. Whereas traditionally, I'm sure that you all run into the scenario where you're delivering code on a weekend because that's what the business demands, and you're there till 3 a.m. making sure the delivery was successful. And that could be a challenge. And if it wasn't, then you're there Sunday as well. So you're there all weekend to make sure that this code that rolls out to production to your customers is available and successful without impacting the business. So if you have automation in place, if you have machine learning in place, you should have confidence and you can trust your pipeline will deliver this successfully. So you're going to release with confidence using AI, artificial intelligence, and machine learning. I think we also realized and learned in this that quality meals require successful delivery. And so for those of you who are going to go out to dinner tonight, maybe think for, as you're waiting for your meal to arrive, well, all those steps that it has to go through to get to you, from the different cooks that are cooking and preparing it, from the dishes that are plated for you, from the people who carry it out to you, ultimately to the point where you're the tester who's going to tweet your successful experience or your miserable experience in your meal. And hopefully you'll have a sweet dessert. So are there any questions?
I think we can open up for questions.
Okay. Well, if there's no questions, what we can do really quickly is why don't we jump into a small demo here. So let me kind of introduce you to Harness for those of you who've never seen it. This will be a fairly quick demo of this, but looking at Harness, we analyze all of your deployments, all the deployments that are captured through the system, including the failures, when they occurred, how many deployments occurred. And you can see that there's fairly high velocity. I mean, we're deploying, 40 or 50, deployments each day. But when they fail, we want to be able to kind of analyze what those failures look like. So let's select the failures here in this deployment, and we see this deployment failed. Let's take a look at this deployment and see what happened. So this is what a deployment looks like. This is all templatized. Actually, why don't I kind of jump over there so you can kind of see the steps of this. When we look at a deployment, it's divided up into a number of different workflows, and each of these workflows has different function. So this is the workflow for dev. So the development is doing kind of a sonar cube scan, and it's rolling this out, and it's doing some updates as well to the to Jira for the ticketing. If we look at our QA, this particular workflow for QA in our pipeline is a little bit different, and this one has some testing that's involved for verification. So it's analyzing against AppDynamics, some Splunk analysis. It's using JMeter and Selenium, and it's also doing a set of regression tests that were defined. So this particular workflow is deploying the order service into Kubernetes. It's doing a rolling deployment, and it's applying those tests once that's completed. And then if we look at, for instance, the production stage, I'll just kind of jump into this one as well. You'll see what this is actually going to do is in this workflow, it's going to do a canary. And when the canary is successful, it'll do a primary deployment where we'll actually do a full rollout of this. However, if the canary were to fail, it'll apply the failure strategy in this case, which is to roll back the workflow execution on application error. So it's actually going to, if it fails, it's going to roll it back to be strictly the current running primary, not the one that's staged and ready to go. All right, so how does this work when we actually go through the deployment? We can see that it fully deployed here. It did our sonar cube scan. Harness captures all of that information. This is not using analysis. This is actually just waiting on whether or not the script was successful, and then it did a rollout. So this is this could be in part of the verification step, but instead this was just a artifact scan of the container. And if it errored out or if it provided any errors, that actually would have caused this pipeline to not progress any further. When we look at the QA environment, this actually did employ the verification step, in this case using AppDynamics. And when we look at AppDynamics, we can actually see the particular metrics that it's analyzing for the endpoint for this webhook. And it's actually analyzing this against it's a new value, so it's not analyzing against any other baselines or anything like that. It's just identifying if there's any problems or anomalies within the data, right, within the data sets. So it's kind of, here's where it kind of expects it to have been, and it succeeded, and not to within the 95th percentile. So there are really no problems found in any of the metrics that it analyzed. When we look at the logging, there was let's see, there's no analysis here that was of an issue. So it didn't have an issue there. We did our regression testing. There's some warnings, but no failures. We did a load test that completed successfully. We also did some Selenium testing, which also completed with an exit code of 0. So these are all successful, and it moved on to the post-deployment. The approval stage was Jira, so it called out to Jira and made it call out to Jira for an approval. Once it was approved, it automatically moved into production. And you already see that this failed, right? This clearly failed, which is why we see the rollback canary. But we can analyze this a little deeper and try and understand what actually happened. So if we look at the AppDynamics analysis here, what we didn't catch in QA, we are catching under load in production for the 95th percentile response time of this particular call. So this analysis diverges here, right? This deviation is occurring, and this is picked up by the machine learning to identify that this deviation is a risk. It's a high risk, in this case, a medium risk, and therefore the AI is determining that alone should be a failure, and so therefore it created a failure state. When we look at the Splunk logs in this case, actually let's look at the out logs. See if I reload the page, if this will give me the detail. This might be just a UI issue. Oh, there we go. So when we look at the Splunk logs in this case, we can see the anomalies that are occurring, right? These are the clusters that we see that are outside of the clusters that we know. So if we remove the anomalous events, you'll see that these are all in places that are not familiar to the AI. And what it's doing is it's actually analyzing this against a previous version. So the new version is this canary, and it's against the previous version that we're looking at. And we can analyze that to identify whether or not these logs are these log errors are something that we should expect or so. What's interesting though is that we do allow for some of the supervised machine learning, whereby you could say, I want to remove these errors from the baseline. I don't want these appearing there, so that we know that these known events shouldn't be there. However, we can also look at the anomalous events and define them more or less. So we can say we don't want them to be a risk, right? Or, which is essentially helping to train that neural net, or we can prioritize them higher, which will increase the priority of these particular errors when they're seen. So the developers know kind of, as if you're a developer, you know what it looks like when errors come up. Whether these are out of memory would be a significant one that I'm concerned about, because that could have severe impacts, versus something that might just be like a misconfigured state or a null pointer exception. So really, this is how Harness is figuring this out. And as once it figures this out and identifies that these have failures in them that are not okay, that's where it initiates the rollback. So that canary rolls back, and what it does, it actually removes the canary in this case. So it's going to delete the canary itself and wrap it up by rolling back the virtual routes for the specific canary, so that all the traffic is going to the known good running version of this solution. Are there any questions on this? Excellent. Well, like I mentioned, if you have any questions, you're welcome to also reach out to me. My email is peter.hack@harness.io. And if you'd like to give a Harness a try, you're welcome to download our 15-day free trial. You can also work with Deepak, who is familiar with Harness and is more than happy to schedule some time to talk to you about it if you need. But yeah, this is where you should be able to deliver confidently with continuous delivery using Harness.
Thanks, Peter. So I'd really like to thank everyone to come here today and spend that 1 hour in from your personal time. And I know things have been really crazy because of the COVID situation. I hope this session was some way useful to you guys. If there's no question, we can call it a day. I'm just going to go around asking if there's anything else that you would require from our side. So I think, yeah, Parmesh.
Yeah, Deepak, thank you for the session. So just we stepped into CI/CD, and this, yeah, I felt happy with that. This is kind of like a new approach I have seen.
Thanks, Parmesh.